Hello everyone. So today we're going to do a flow around the cylinder. I actually made this. I had an attempt at this video a couple of days ago, but I made a mistake, and I will tell you guys about that mistake. It's quite fundamental to CFD. So okay, let's get on with it. So I've just I'm trying. As I'm going through these videos, and I'm going through my own journey of CFD. I'm learning how to actually do a CFD study. Now, the first thing you should do, or one of the first things, because I'm still learning, is whatever your study is about. So today is about a flow around the cylinder. What you need to do is find the flow physics around that object, the flow physics about that object, whatever you're doing, right? So there must be like the theory, the fundamentals, the laws, the facts, whatever about that example out there, okay? So that when you do your CFD study, you can validate, verify whatever it is, right? With that theory, those equations, those laws, etc. Okay, so the first thing I did was go on Google, type in flow around the cylinder, and as you can see there, I got a couple of pictures and whatnot, diagrams and schematics explaining the stuff. I chose one. It brought me to this page here, and I will share the link of this page in the description with you guys. But anyways, when you do ask this website, it tells you what the flow physics would be around the cylinder. So, or tell you what a no separation flow would look like. I'm guessing this is the ideal scenario, because if you don't have any separation, this is where you reduce the drag to maximum. Okay. So in steady separation bubble, this is what you would get, the sort of flow in the CFD. And in oscillating von Karman vortex, you see vortices that are going up and down as you come in. Of course, we will run a transient study today, so you can actually see these oscillating Karman vortex street wakes. Okay, we'll see that. And so you got the laminar boundary layer and the turbulent boundary layer. Now the difference between the two is you can see here the flow sticks to the cylinder for a lot longer. So you see here the flow separates earlier, the flow here separates later. Okay, so that's why on aircraft's wings and whatnot, maybe even on aircraft engines casing, you would see little vortex generators. If you search that up on Google, vortex generators, you'll know what they are. They have that on the wings and the engine casing I've seen, I think, where it makes the turbulent near the skin, you can say, or the surface, turbulent. The boundary layer make it turbulent, and that makes it stick to the surface for a lot longer, which means you reduce drag. And I find that quite fascinating, because you would intuitively think that laminar would be the best, right? You want it to flow to be as laminar as possible, and that would be the best. But it turns out that turbulent is the best. So turbulent is not always bad. People say turbulence is bad. It's not always bad. Turbulence is good for mixing, right? In engine cylinders, you want turbulent flows because that will increase the mixing, right? And you want the air and fuel to mix as good. The better it mixes, the more efficient it is. Okay, that's why in engine cylinders you see that they have these geometries such that the flow comes in and makes it turbulent. And the three characteristics of turbulence are mixing, chaotic, and the vorticities are distributed in all three dimensions, X, Y, and Z, irregularly. Okay, so these are the three characteristics of turbulence. So the flow is chaotic, you cannot reproduce it. The flow is chaotic. It mixes, so it mixes quite well, the flow, and it's what's the other one? Chaotic, mixing, and the vorticities are distributed in all three dimensions. Okay. So, anyway, this is the flow. So today we're going to be running say a turbulent example. And I'll use this spell out Almirez turbulence model because that's what they use for external flows like wings. It's quite good for that. Ideal. Again, you can search that all about the model and stuff. It's too in depth. Okay, so I'll share the link to this website for you. So you should expect something like this in our CFD study. Okay, or something like that. Sorry. So you're going to see that one Kalman vortex at the back and turbulent flow. Okay, so you go down here, you got shockwave problems, and here it explains a lot more stuff here. You've got a bit of theory, a look in-depth mathematics and stuff, right? And you're going to get two stagnation regions. And so where the flow is basically not moving. So the pressure is going to be really, really high, okay? Because when the pressure is high, velocity is low. When the velocity is high, the pressure is low, okay? That's how it is. You can manually equations, you will work that out, okay? So let's get on with the solutions or the simulation. Okay, so we're going to go on ANSYS Workbench. We are going to open up ANSYS Fluent. So you just click it, drag, and drop it in this green area. Let go of the mouse, and then here it is. Okay, so we don't need to rename anything, but if you want to rename, you can just use this little drop-down list here, rename and stuff, right? We're going to use ANSYS Space Claim. We're going to right-click, open new ANSYS Geometry Space Claim, click that. And this video might be split into two different parts. Part one, I think I'll stop at the setup, maybe at the solution phase, and I'll run the solution in the second part. Depends how much time we have left, where I get up to. Okay, so we're in Space Claim now. First thing we're going to do is we're going to click here as we go normal to the plane. There we go, normal to it. And we're going to click on the rectangle. We're going to click on the origin and just move your mouse. And then you can, so you're going to use the tab key to switch between these two. Tab key on your keyboard. When you go on here, we're going to say 100. Press the tab key. And then we're going to go on, let's say, 200. And you're going to press enter. Okay, so here we are. Okay, so now we have this. Or I might extend it a bit more. If I go on dimensions, I go on this. Okay, you go and click this. You can make this to 300. Okay, and that's that now. Press escape on your keyboard. Now we're gonna choose the circle to get our cylinder. And we're gonna place our cylinder. This is just a rough study, so we don't need to go too much into it. But place our study, let's say, the cylinder sit here. And we're gonna dimension it. Okay. Dimension. I'm gonna give it, let's say 30 mil. Okay. So that looks like 30 mil. Oh, it's not doing it. Okay, let's delete this. Try again. Go here. We go on 30 mil. Okay. Now you have our 30 mil cylinder, and we can dimension it. Dimension it. So we're going to go on here. Here it's going to be 50 mil. 50 mil. Okay. And then from here to here, it's going to be 50 mil. Okay, as you saw it moved. Okay, and that's our cylinder. Now you can just press escape, press this pull thing, and this thing goes like that. Okay, then I don't need to do anything, just press escape on the keyboard. Okay, but the mistake that I did last time was I left this cylinder in there and I put this as inlet, outlet, and I thought the flow would go in inside. I named this as the wall. I thought the flow would go inside and it would go over the cylinder, but that's not how it happens. In CFD, you only want the fluid domain. You do not want the structure. Okay, so remove the structure. Where the structures are, you just basically don't have anything there. You put a hole. Okay, so if I left this in there, the flow will just come in and it will go straight through. But if I remove this and make this a hole, that's the only way this flow would come in and it would go over. Okay, so in CFD we only need the fluid domain. We do not need the structure. So we're going to remove this thing. Okay, we're going to remove it. So we're going to do something go like this. I'm going to click on detach and then delete. Okay, so detached, made it two surfaces and then deleted one of the surfaces. So now we have our cylinder. Okay, that's our cylinder. We do not need structure. We only need the hollow region here for the flow to go around the cylinder. Okay, so now we have our geometry done. We can exit space claim, so we can just either save this or you don't need to save it. You can click on close, press the cross at the top right, and now you can double click on the mesh. Okay. Okay, so now we are in the meshing window. Okay, you can go normal to the surface again, press the Y and it goes normal to it. We have our one surface here. Okay, material doesn't really matter. Okay, meshing we go on and we just generate the initial mesh, see what the system default is. Okay, so we just press generate and this is the default. It's not golden. Okay, we will definitely won't see the von Karman vortex here with this type of mesh. It's too coarse. So we're gonna go on here. We're gonna, let's say, apply sizing. Sizing around this, and then let's press that. Okay, so we're gonna make it 0.001. Okay, so now it's much better. We're gonna go insert, we're gonna go on inflation. We're gonna go on here, go there, and press enter. Okay, and let's reduce the mesh size to 0.001. I think it'll give me an error might be because this thing needs to be smaller than the actual global mesh, or equal to, I think. But let's see what it gives. Okay, so after putting the inflation, the edge sizing, basically what it did was reduce the mesh length, you could say, the element length around the circle, so when it grows out, it's a lot smaller. You can see before it was quite large, the length, and when I reduced the edge sizing, it became smaller, the distances. Inflation does the same, so it does it around the whole thing. So around here, it will grow out, slowly. Okay, so that's what the inflation does. And now I'm going to do is apply method, and we're going to click on this whole region, and we're going to choose method to be multi-zone. So you allow it to use whatever it likes. Okay. Okay, so I'll see you guys in the next video. Okay, time's running out, so I'll see you guys in the next video and go through this further. Okay.